Okay, in this topic, in this video, we're going to start developing the third major topic in calculus. We've looked at limits, that's one topic. We've looked at derivatives, that's the second topic. And what we're going to start looking at now is integration or integrals. Before we get into defining that, let's just start creating an intuitive understanding of integrals. So starting off with this problem up here, you walk 3 meters per second for 2 seconds, and then 1 meter per second for 2 seconds. How far would you walk? Well, we know how to do that using our understanding of physics. So you walk 3 meters per second for 2 seconds, and then you walk 1 meter per second for 2 seconds. So what we're doing is we're saying that distance equals rate times time. And we can add these together, 6 plus 2, and we get that we went 8 meters. Well, what would that look like graphically? So if we think about time down here and velocity up here, where velocity is the same thing as our rate, well, we're going 3 meters per second for 2 seconds. So let's say that this is 1 and 2 and 3. So for the first 2 seconds, and let's say this is 1 second, 2 seconds. Oops, that's not going to work for us. So 1 second, 2, 3. So for the first 2 seconds, I'm going 3 meters per second. So for the first 2 seconds, we could express our velocity in terms of that line here. We're going 3 meters per second. We're going 3 meters per second for 2 seconds. And then for the next 2 seconds, I'm going 1 meter per second. So we would graphically show that from seconds 2 to 4 like this. And then what we want to do is graphically show the distance. Well, distance we know is rate times time. Well, we've got our velocity or our rate times our time. So what does that look like? Well, that's really just this box, this box that I'm drawing here, which has the dimensions of 3 meters per second times 2 seconds. And if I multiply those together, the dimensions here, 3 meters per second times 2 seconds, this shaded area, this red shaded area here, equals 6 meters. And now let's look at my second portion of the graph where I'm going 1 meter per second for 2 seconds. Again, if I were to make this box, that box has the dimensions, also 2 seconds. Only now I'm only going 1 meter per second. So that area underneath the curve, the area underneath that curve, if I multiply my 2 seconds times 1 meter per second, that area is 2 meters. That's the distance I went. So the total area under the curve, under the two velocity curves, equals 8 meters, and it equals our distance. And this idea is really, this is the idea of integration. What we're looking at is area under the curve, and the area under the curve represents my x value times my y value. So now let's extrapolate this a little bit. So we said that instead our velocity graph was a meter per second for 1 second, and then 2 meters per second for 1 second, then 3 meters per second, and then 4 meters per second. So each second I'm going faster and faster and faster still. So to show this graphically, let's say this is 1, 2, 3, and 4, and this is our velocity. And down here is our time. And let's increment, let's have each of these be a second. So here's 1 second, 2 seconds, 3 seconds, 4 seconds. So from 0 to 1 second, I'm going 1 meter per second. And I express that graphically with this curve. And that's my velocity. Between 0 to 1 second, I'm going 1 meter per second. Then I'm going 2 meters per second for a second. So in between 1 and 2 seconds, I'm going 2 meters per second. And then I'm going 3 meters per second for a second. So in between 2 and 3, I'm going 3 meters per second. So I'm creating like this step model. And then from 3 to 4 seconds, I'm going 4 meters per second. And I express that with again, a horizontal line, meaning that it's a constant velocity of 4 meters per second for that second. So this is a graphical representation of my velocity as a function of time. Well, how far did I go? Before we look at the graphical representation, let's just think about, I went 1 meter per second for 1 second, and then I went 2 meters per second for 1 second, and then I went 3 meters per second for 1 second, and then I went 4 meters per second for 1 second. So the total distance I went, add up each of those, I went 10 meters. And that's using our distance equals rate times time. But this new idea that we're adding is we can find the area underneath the curve. Because if I find that this combined, well, let's start off with my first area. This area right here, that means that I was going 1 meter per second for 1 second. And so that area represents that area represents 1. And then from 1 to 2 seconds, I'm going 2 meters per second. And so that area underneath that curve represents going 2 meters per second. This is the vertical. This is 2 meters per second for 1 second. And so that area underneath is 2. And then from 2 to 3 seconds, I'm going 3 meters per second. And so that area here represents, velocity, which is my y, velocity times my time, and that area, 3 times 1, is 3. So between 2 and 3 seconds, I went 3 meters. Going back between 1 and 2, I went 2 meters. Between 0 and 1, I went 1 meter. And these are my distances represented by area underneath the curve, because the area underneath the curve is my velocity times time, which we know is distance. And the last one, just to finish it out, from 3 to 4 seconds, I'm going 4 meters per second for 1 second. And so that area is an area of 4. And so the total area under the curve, if we add up all those, is the same thing as we get above. 1 plus 2 plus 3 plus 4, which equals 10. So the area under the curve, when we're talking about velocity and time, is our distance. Okay, well, now let's extend this a little bit further. We've got these points. Their time and velocity, and the situation is a child sliding down a giant water splash. So we're having some fun in the summertime, and we want to sketch a velocity time using these points. So if we go ahead and start plotting these points, the first point we have is time is 0, velocity is 2, and 2, 3.9, 4, 5.4, 6, 6.6, and I'll go ahead and just plot the next 2 points. So we have our points plotted here, and next thing we have to do is start answering these questions. And the important thing for us to recognize is that all we know, the only thing that we know is that we know the velocities at these given times. And we don't know what's going on in between 0 and 2 seconds, for example. So in between 0 and 2 seconds, we don't know how, what's the velocity at 1 second? We're not sure. What's the velocity at 1.99 seconds? We're not sure. All we know is that at time 0, we're going 2 feet per second right here, and at time 2, we're going 3.9 feet per second. That's the only information that we know. And we can assume that, they're getting faster and faster and faster based on our data. We can assume that, but we don't know that. So it says, so if we answer B, based on the table, what's the minimum possible distance traveled during the first 2 seconds? Well, the minimum possible distance, if we were trying to find the minimum, is that we would assume, and here we make some assumptions, we would assume that the minimum possible distance, and we'll draw it in green, is that for almost the entire way, the kid was going 2 feet per second, the smaller of the two velocities. So our minimum possible distance would be that it's going, and this is the green box, 2 feet per second for 2 seconds, which is 4 feet. That would find the minimum distance. And again, we're assuming that we're going the slowest velocity for the longest time. What would be the maximum distance? Well, let's do that in blue. The maximum distance would be to assume that we were going this velocity for the majority of the time. That for almost the entire time we were going 3.9 feet per second. And we would express that by drawing this following box. So our maximum distance would be assuming that we were going 3.9 feet per second for 2 seconds, which equals 7.8 feet. So in other words, our minimum guess is that we went 4 feet using the fact that we were going 2 feet per second for 2 seconds, the lesser of the velocities, and our maximum distance approximation for the distance would be 7.8 feet, and that's using our greatest speed throughout the whole time. Well, we could go out and continue to make, minimum approximation for the total length of the slide and a maximum possible length for the entire slide. And we'll do that now. So for each of the minimum we're going to do in green, and the maximum we'll do in blue. So between 0 and 2 seconds, we've already figured it out, what the max and min. Now let's look between 2 to 4 seconds. Between 2 to 4 seconds, we're going to use our minimum distance. So we're either going to use 3.9 or 5.4. 3.9 is the smaller. So let's draw a box here, go down. And so our minimum distance between 2 to 4 seconds is 3.9 times 2, which is 7.8. Notice that that's the distance we got there. And from 4 to 6 seconds, again, between 4 to 6 seconds, I can either use 5.4 or 6.6. I'm going to use the lesser one because we're looking for the minimum approximation. So we draw this box in that area. It's going to be 5.4 times 2. And I'm going to stop this video and we'll start a new video. Timing wise, we need to make a new video.